In the last part of Section 12, we'll talk about some collisions that we have seen and witnessed. These are a great sequence images from the 1994 impact of comet Shoemaker-Levy 9 crashing into the atmosphere of Jupiter. If you look just there, you can go ahead and zoom in on this. You can see the initial impact. And it's creating this giant fireball on the surface of Jupiter. And that left this scar almost, this storm that's now been formed by the impact energy. This is only a few hours later. Here it is 5 days later after the original impact. And this is a span of clouds stretching thousands of kilometers now. Here's an example of a comet that probably exploded in the atmosphere above Earth but close to the ground. These are images from 1927, about 20 years after the original explosion, where all these trees were just tumbled over. This is in Tunguska. And image about 100 years later, you can still see what looks like an impact, but this thing never actually hit the ground. It was up in the air when it exploded and fell apart. So even 100 years later, the trees in this area actually grow at a slight slant because of the amount of energy released before that object even hit the ground. A more recent example is one in 2013, where a meteorite exploded over Chelyabinsk, Russia. When it exploded, buildings in 6 cities were damaged and almost 1,000 people were injured, but thankfully no one was critically harmed or killed by this. And for whatever reason, people in Russia tend to have lots of dashboard cameras on them, and so we actually have lots of great footage of this meteoroid, right, as it basically evaporated in the air. So let's go ahead and cut to the footage of that. Let's go ahead and let this video play. This is from a dashboard camera, and you're going to see from the top left corner the meteoroids start to come in, crashing through the sky. Alright, there it is. And as it's burning up, friction is causing this thing to quickly heat up, and now here comes the explosion. It suddenly falls apart, breaks away, and only tiny pieces actually crash down onto the Earth's surface. Still a lot of damage caused by even just that flying through. So let's get our terminology correct here. A meteoroid is something that's floating around in space, most likely chunks of comets or asteroids that have broken off, just the fragments. The meteor, which many people often refer to as shooting stars, is anything that is flying through Earth's atmosphere and burning up. And you get that characteristic trail of material behind it. What's happening is that as the meteoroid enters Earth's atmosphere, it becomes a meteor, and that meteor is getting frictionally heated as it's passing through the atmosphere, getting thicker and thicker layers. It's getting heated up, and chunks of this meteor are falling off behind it and just disintegrating the atmosphere. Now, any meteor that's big enough to survive burning up through our atmosphere and crashing onto the Earth, that's one of our meteorites. And these are the samples that we'll find scattered, especially near craters amongst the planet's surface. Now let's talk about how much energy is released when a meteoroid crashes into the surface of the planet. And to put this in perspective, let's take a meteoroid that has a mass of 1,590 kilograms, and it's moving at a brisk 20 kilometers a second. Put that number in scale. This mass is about a tiny car. Just have a small car, but moving very rapidly. For reference, this 20 kilometers a second is roughly the launch speed of the New Horizons spacecraft. So it's not a very unreasonable calculation that we're doing here. These are speeds that we have achieved by just throwing things up into space. So the question is, how much energy is released upon that impact? Well, we're going to need something called the kinetic energy of the meteor. We've talked about examples of like gravitational energy. The higher up something is, the more energy it has when it falls down and slams on your foot, so on and so forth. Another type of energy is just the energy of motion, or kinetic. And it goes as 1/2 the mass of the moving object times its speed squared. So the faster the object's moving, the more energy it has. So let's just plug in the numbers and calculate the result. We'll say 1/2 mass of the meteorite, 1,590 kilograms, times its speed. Converting it into meters per second, it'll be 2 times 10 to the 4th meters per second squared. And it'll get the result of 3.18 10 to the 11th joules. All right. I mean, we're happy we've solved the problem, but I know everyone's scratching their heads going, okay, that's a big number. Let's move on. Well, let's not move on. Let's try and put this number in context. All right, what is 10 to the 11th joules mean? If I have, say, one stick of dynamite, just one stick of dynamite, I set it off, boom, either blow my arm off or set it to detonate a building. All right, that one stick has what is called 1 megajoule of energy, or 1,000,000 joules of energy. So if I recast this, the energy of the meteorite that is crashing into our planet in terms of megajoules, that 3.18 10 to the 11th ratio by 1 megajoule is equal to 3.18 10 to the 5th joules, or 10 to the 5th sticks of dynamite. Let's get our units right, because this is joules, this is number of joules per stick of dynamite, so here's a stick of dynamite's worth of energy. What we're saying is that this meteor impact, just this tiny car slamming into the surface of the planet, is equivalent to 318,000 sticks of dynamite. So much energy is packed into this rapidly moving object. Sometimes we'll see amazing pictures like meteor showers. What these are is Earth's atmosphere just passing through debris that's just floating out there, and we just happen to be going through it. If you have a single piece, you're going to get sporadic meteors. And as that material is interacting with our atmosphere, the individual debris is just going to start burning up. And that's why we see these beautiful streaks. It's that material getting bombarded by the big mass of Earth falling in through it. Some of these can happen very annually. There's the Perseids Showers seen here, and they happen around every mid-August. And this is because Earth is passing through debris left by the comet Swift-Tuttle. As the comet Swift-Tuttle went by, it just left a cloud of material out there. So every year, we just pass through some of that. And that's why we always get these annual showers. Another effect that we can get from just the debris floating out there is stuff that isn't crashing into our atmosphere, creating meteor showers, but we can get something called a false dawn, and this is a perfect encapsulation of this. What's happening is that sunlight is reflecting off the debris left over from comets or tiny fragments of an asteroid. And that's producing what we call this zodiacal dust. So this you see here is the dust from the comets and asteroids that have fallen apart. And as the sunlight tries to reflect through that, it will get deflected, creating this zodiacal light that here on Earth we'd call a false dawn. So we've seen how collisions can have huge impacts, and just they're tiny. They don't even reach contact with the Earth. They just explode over the surface. So as a encapsulation of all this, we can say that the comets and asteroids have affected life on Earth in the past and could in the future. Comets most likely, when there are big icy planetesimals, probably deposited the bulk of the water that we find here on Earth. Another thing that we can see in comets is the potential for complex organic matter. It is possible that life rode here on Earth on a comet and just it formed somewhere else. And once it landed on Earth, had enough A, material, and B, external energy, our sun, to let it flourish. So it is possible that life is actually able to travel through the vacuum of space, just hitching a ride on a comet flying around out there. So now we'll end this section as just a in-cap reminder, test your knowledge, see how awake everyone is, and just say, here's a picture of a comet, A, B, C, or D. Which one is pointing towards the sun? Might need to go back a video or freshen up on your material. But we'll say that it's A. Remember, you have this dust tail and the ion tail. And the ion tail, that's the one that's pointing towards the sun at all times, because the ion tail is getting blasted away by the solar wind. As a brief summary of everything we've talked about in this section, recall, dwarf planets are planetesimals. They are massive enough to be spherical, but they have neighbors. They haven't cleared the orbits around them, and they can have all sorts of interesting properties with them. But in essence, they are massive enough to be a sphere, but did not clear the neighborhoods. That's the emphasis of a dwarf planet. And we keep finding more and more of these things. Going beyond that, we had our asteroids, and we broke them up into three main categories: the C types, the S types, and the Ms. C's being the most common, S next, Ms. C's were carbon-based, the S were silicates, stony rocks, minerals, and Ms being the magnetic metals, iron, kind of nickels. That's the kind of stuff we're seeing in these asteroids. Comets, as I like to say, are basically snowballs, and when they approach the sun, they start to melt. So we had two types of comets we discussed: the short period that live in the Kuiper belt, and the long periods that live out in the Oort cloud. And a lot of these objects are going to pass close or pass near our atmosphere, and so the terminology that we use is that if it's in space, we call it a meteoroid. And this is a blanket term. A comet or an asteroid can meet the definition of a meteoroid. If it's burning up through our atmosphere, it's a meteor. We talk about meteor showers, where you get the bands going through. And our last category is a meteorite. That's material that has hit the surface of the planet, and for us, gives us great opportunities to pick them up and study them. So that, we'll call it into section 12, and I'll see you all next time.